Shall I put this off just a moment? Meeting options. Good. So yesterday we were discussing about the mathematical model, the cellular model. So where there is a detailed procedure of cell migration, proliferation, and cell differentiation from mesenchymal cells, MSC, from fibroblast cell, from chondrocyte cell, from osteoblast cell. So how each differentiate, okay, based on the biological event that we have actually discussed earlier. So biological events of mesenchymal cells getting differentiated into fibroblast, chondrocyte, and osteoblast. Each fibroblast can also differentiate into chondrocyte and osteoblast. So from fibroblast, it can differentiate into chondrocyte, to osteoblast. Chondrocyte can differentiate into osteoblast, but not the reverse. Okay, and each will produce different kinds of tissue. Fibroblast can directly liberate or produce fibrous tissue. Chondrocyte can produce cartilage. Osteoblast can produce bone, as you all know. Okay, bone forming cells produce bone. Now, if we go to the mathematical equations, first term is migration, second term is proliferation, and the others are basically 1, 2, 3 negative terms are the differentiation, cell differentiation. Of course, it includes the cell death, so that is also a negative term, right? So I've explained each of the terms. So from mesenchymal cells actually form fibroblast, chondrocyte. So FF, the small f stands for fibroblast, C stands for chondrocyte, B stands for osteoblast. Okay. So from mesenchymal cells, you get all three. Of course, there is some cell death, apoptosis. So when you consider fibroblast, the sequence of event, the chondrocyte that is liberated, the fibroblast cells that is differentiated from mesenchymal cells will be added here. Okay, but fibroblast itself can differentiate into chondrocyte and osteoblast. So that is clearly mentioned here. There will be another slide later on coming for this. Similarly, this chondrocyte cell that has been differentiated from fibroblast will be added here. This coefficient is actually incorrectly typed. Can you notice this? The plus FC 1 minus CC into CF. This CF should have been here. This needs to a little bit of typing correction. Okay, can everybody notice that? Did everybody notice that? I'm just trying to draw your attention. Did everybody notice that? I'll just put it on.
Yes, sir.
Yeah, there's a small typing error there. Okay, I hope it doesn't cause too much of a problem. Is that correct? Have you corrected it? All?
Yes, sir.
Yes, sir.
Yeah, please note that. Don't make, don't take it as a holy equation. Okay? There may be some typing errors. We are human beings. Okay? So you can easily correct that because it's not too difficult to correct it. I'm going back to the presentation. So we can write down the differentiation and the total, mathematical modeling of the biological events of migration, proliferation, and cell differentiation, as well as cell apoptosis, cell death, basically, by these differential equations, partial differential equations. And each and every, you see on the left, basically is the concentration of the cell type that is being differentiated. Okay, and the terms like CF, CM, CC, all these terms, CB, they are basically coefficients that govern the process. So all the coefficients depend on mechanoregulatory principle. There are some detailed documentation on that. So from cell concentration to bone tissue, as I was telling you, when you are trying to model explicitly the different types of cellular mechanics being included in an elaborate model, you need to also find out the mass, differentiated mass of bone tissue, differentiated mass of cartilage tissue, differentiated mass of fibrous tissue. So we were discussing yesterday about single phase representation of the bone tissue as a single phase material, also as two phase material. But if you are going into the detailed two phase modeling approach, you need to actually model or include in your model the porosity of the tissue, the permeability of the tissue, and the interstitial fluid velocity. Okay? So, interstitial fluid velocity, permeability, and porosity of the tissue needs to be modeled. Okay, but we have done that in the paper. I will go to the paper a little bit later. Otherwise, it will all become too confusing for you. But if you are trying to model it as a single phase continuum, continuum representation of bone, but numerically modeling the porosity, not physically, then stress invariants like octahedral shear stress and hydrostatic stresses, they can be used quite efficiently to decide which tissue is being formed, what type of tissue is formed, okay, based on the mechanoregulatory principle. So I discussed this thing yesterday. One important paper, as somebody asked me in the class, that the relevance with biological events. Clay's et al. 1999 was a pioneering paper contribution, and this group, basically from Germany, and they have done a lot of work. Okay, so there is a group from Ulm, ULM, the University of Ulm, plus the Charity University, the Charity in Berlin. There are very strong groups who continuously working for decades on bone regeneration models. And remember that any proposed model needs validation. Okay, needs to be validated, verified with biological experiments. Things are not published just like that. Okay, so if a paper comes to me for review from a good journal, the first question, if I see it as a numerical work or a proposed sort of mathematical modeling approach, the first question what we pose as a reviewer, without even reading the paper, is how do you know that your formulation is correct? How do you know your results are correct? Prove it. Okay, that is very, very usual. It's a common practice. So any publication, good publication of course, goes through that check, that the check of verification and validation before it can be accepted as a worthwhile contribution. So these values basically based on principal strain and hydrostatic core pressure. Actually, there are some threshold values or threshold range of values based on which we can actually decide whether or not this tissue is a fibrous tissue or cartilage or immature bone or mature bone. Now, if you consider a two-phase porous material representation of tissue, then you actually need to calculate an index I, okay, which combines the deviatoric strain and the fluid flow, both. Okay, it doesn't have a directly some values like principal strain and hydrostatic. This has an index that combines deviatoric strain and fluid flow. Okay, and when it combines based on I is equal to greater than 3, it is actually fibrous tissue. I greater than 1 is actually cartilage. I greater than 0.267 is immature bone, and mature bone is 0.01. Okay. Now, what you can conclude from this number, that as there is increase in the number, the whole tissue becomes more softer and softer and softer. If you see that, look at the index value. The least value is 0.01 here, mature bone. Then slightly more is immature bone. That means already the transformation from soft tissue to hard tissue has occurred in that range. Okay. The more the tissue gets softer, see here, from immature bone to cartilage, which is something in between soft and hard tissue, something in between, that is 1 greater than 1. But anything greater than 3 times softer actually than cartilage is fibrous tissue. Okay, so you can already conclude some physical properties from here. Now, if you are using the phenomenological model, the model, say, the one here, phenomenological model, the shortcut model where it does not actually explicitly model proliferation and migration, but a combined modeling approach of using the diffusion principle. You can, this is basically cell concentration. So from concentration, you can actually directly go to the modulus. So you update the modulus of the tissue. So from granulation tissue, there will be an iterative procedure by which a newly formed tissue layer, the modulus, will be updated. Okay. Then, there would homogenization principle is applied. That is also based on this paper, Lacroix and Pendergast 2000, to actually smoothen the whole changing E modulus of the tissues, adjacent tissues. So a smoothening effect is applied using the homogenization principle. And as I discussed yesterday, the equilibrium condition is achieved when two subsequent iteration, yielding two different values of E modulus is less than a certain tolerance limit. So single phase material versus two phase material, you can see the phenomenological model being used, single phase material, known as single phase material. and bone as two-phase material or tissue as two-phase material, but same procedure, phenomenological one. Okay? Just see, this is a 2D simulation done long back. Okay? But if you use the same method, but consider it, the tissue as a two-phase porous material, you can see the difference. So one is a phenomenological model with two-phase porous material. The other is a cell-specific model with two-phase porous material. But very important result that needs to be noted here is if you compare the outcome, the final outcome, when equilibrium has been achieved, okay, equilibrium in tissue differentiation have been achieved, the final outcome, there is hardly any difference in the newly formed tissues. Okay, very, very minor differences if you observe, as I am pointing with my laser pointer, the day 18 slide, okay, top and bottom. If you compare, you see almost similar, only there is some differences in the green here. So with this knowledge, we actually started this whole new complex set of events of tissue engineering, mechanobiology principles. We set out to investigate that what really happens. You know, different people have come up with simplified models, but they had one thing in mind. Say, when you are actually using an uncemented implant, the fixation of the uncemented implants hugely relies on bone ingrowth, because there is no other foreign material that is aiding or facilitating fixation of the implant with the bone. So bone ingrowth, say within, say a femoral stem or acetabular cup, is sufficient bone ingrowth is vital for the outcome of the reconstructed surgery. Am I clear to you? Let me stop here and get some feedback. Hello, my friends. Any questions at this point? Students, I have put you on. Hello. Can you hear me?
Yes, sir, we can hear you.
So, any question at this point? Else I will continue. Okay. So let me continue. Right?
Yes, sir.
Yeah. So let's get back to where we were there. So this is where the work started. So we have a host of uncemented implants, rather porous coated, cementless variety of implants where, you know, were evolving in the market, and there was a huge interest in using these implants, which can actually rely on biological fixation. So biological fixation depends on amount of bone ingrowth at the interface, that is where you have this porous coating. But how to quantify that? Quantification of the amount of bone ingrowth was very much necessary to assess not only the design of the implant, but also the design of the porous coating. Okay, because overall, you see, you have realized by this time that the mechanical environment is influencing bone ingrowth as well as bone adaptation. Now, there is a local effect, there is a global effect. The mechanical environment is grossly influenced by the overall design of the implant as well as intricate design of the porous coating as well. If you search in the internet, do a literature review on the types of porous coating, you will already get quite a range of different designs that has evolved in the market that will actually ensure better fixation through mechanical interlocking that is formed between the porous coating and the bone matrix. Okay? So with this idea in mind, we had set out to investigate that how numerically we can simulate this process to get hold of a spatial distribution of the evolutionary bone ingrowth phenomenon. So we had done some work on acetabular implants, pelvic bone replacement. So to start with, we concentrated, our focus area was the acetabular prosthesis. So you can see that a very basic type of acetabular cup, inverted of course, and you can see already beaded structure. You see the beaded structure, which are actually nothing but a part of the prosthesis, but it is porous coated under surface that is forming the interface with bone. Okay, you have different types of coating. The beaded surface can be also found in femoral stems. There may be lattice structured implant on the as a porous coating. So many things have evolved in the market, but the question remains what parameters can actually influence the amount of bone ingrowth. For that, we needed to do a complete numerical investigation. Preclinical investigation was necessary. So, with all the theory and review of literature, we set out to develop the fracture healing algorithm. Okay? And we applied that algorithm on, say, uncemented implant. It was actually the implanted pelvis. Okay? On the left, you see the femoral implant, uncemented. So implant porous coating bone. If we zoom in into the interface area, so we actually took up one very small element, a micro scale model of the implant tissue and bone interface. And you can see that this figure in the middle consists of clearly 3 zones, if not 4, because the implant has the body of the implant. Excuse me, please. So you have the body of the implant and you have the bead. Just a moment. Okay, let us continue. So we have the red area, where red area can be subdivided into two different areas. One is the implant body, another is the implant bead. The bead is the part of the porous coating, but that is an integral part of the prosthesis. So they are all marked red. Now the blue area, the blue zone, is the granulation tissue that is formed in the interbead spacing, right? And on top is pure bone, right? So you have basically three clear zones. One on top is the bone, pure bone, matured bone or the bone. Then in between is a layer, sandwich layer of granulation tissue, which is formed in between the interbead spacings. And of course, then comes the beaded structure and the implant structure. This is what is the microscale model of the implant tissue bone. So this is another, example, just to give you that the people have actually investigated on dental implants as well. Okay? Because in dentistry or dental implants, there is a huge application of uncemented implants. So people have tried with simplified 2D models with dental implants, then cortical bone, cancellous bone, and healing, the granulation tissue layer that is formed in between or at the interface of the implant bone. More examples. See, this is typically a section of the resurfaced femoral head or deep resurfacing or femoral resurfacing implant. So you can see that this is the implant, the dark gray, as I'm pointing you out. So it is cemented with C. And before you insert this implant, you need to rim a hole. So an over-rimmed hole is first drilled into this bone, which serves as a guide, and this stem actually needs to be placed at a predefined angle inside the hole. Okay, over-rimmed hole. It is an over-rimmed hole, and there is a taper. You can observe that there is a taper in the stem that is going inside. So what does that mean? That there is gap is created at the end or the distal part of the stem or distal part of this hole. There is gap already, implant bone gap. Of course, a gap doesn't remain as a gap for a long time because bone tries to grow inside this gap to fill up the gap. So bone is a natural material. It always tries to repair itself if there is any place to repair. Okay, so for different applications, people have tried to investigate and get hold of how tissue actually transforms itself or differentiates itself at different times. Another application is the polar gap. So in case of acetabular implant, you try to first machine the bone in order to place the prosthesis, but you rely on peripheral fit, press-fitted acetabular component placement, leaving a gap towards the pole. Okay, you can see variable gaps at the pole of the prosthesis, towards the pole of the prosthesis, for different kinds of design and press fitting of the implant. Okay, so this is the acetabular bone, and there is this acetabular liner, basically the acetabular component, and then the acetabular cup. It may be a polyethylene cup, it may be a solid thing altogether, and then the femoral head. Okay, but the acetabular implant is actually the liner and the cup together. But whatever you do, you have to fit this acetabular implant into the acetabular cavity, which is already reamed to fit the implant. And if you are using an uncemented, which is mostly an uncemented implant, acetabular implant, you generally press fit it. And the press fitting relies on peripheral fit, as you can see here, leaving a gap at the polar side. So, we set out to develop a computational framework to implement the mechanoregulative tissue differentiation algorithm. So, as I had discussed earlier, we had two models. One is a simplified phenomenological model. Another is a more elaborate, more detailed self-phenotype specific model. Salient features of phenomenological model were it is diffusion-based modeling. Cell differentiation is governed by a mechanoregulatory principle that I have explained with the table. Explicit tissue formation is not modeled here. So there is no mass of tissue formation being calculated here in the phenomenological model. The mass of tissue formed that we had shown you three equations corresponding to bone, fibrous tissue, and cartilage, that corresponds basically to the cell phenotype model. Okay, I'll just go back very quickly to show you again what I meant. Yes, this slide. So the tissue form, mass of tissue formed from different concentrations can be only obtained in case of cellular model, because bone, cartilage, fibrous tissue. Okay, so the concentration separately can be obtained if we use this set of equation, not just the shortcut method. Okay. In comparison, the cell phenotype actually explicitly models cell migration, proliferation, differentiation, and apoptosis, or cell death, explicitly and separately. Okay? Extracellular matrix formation and tissue degradation are considered in this one. Certainly considered in this. And the coefficients of all the biological phenomena are governed by mechanoregulatory principle. Okay. These are the salient differences in the features of these two types of modeling approaches. Now, as you all know, that the mechanical factors that govern periprosthetic bone ingrowth are surface texture design, material property of bone and implant, and most importantly, the boundary conditions. All these three together actually influence the mechanical environment, thereby periprosthetic bone growth. Just the repetition of the slide that we have used for our simulations. So here you can see the rho has been replaced by C. So cell concentration is directly using, is already there in the diffusion principle. The equations, same equations as we have explained to you. Now here is the migration term. Here is the proliferation term. This is cell differentiation. As I have already explained you, this is cell death or apoptosis term. Okay? Further, you can calculate the differentiated bone tissue, cartilage tissue, and fibrous tissue. This is tissue formation, this part. This is tissue degradation. Okay? So explicitly tissue formation and tissue degradation is modeled in the cell phenotype specific algorithm.